Okay, what does a unit do, computationally speaking? Well, first, it must compute the total signal sent to it by other processors or other units. Second, it must adopt a particular level of activation based on the net input signal. Then it must generate its own signal based on its activation level. And then, finally, it must send an output to the other units. To do this, it must employ at least two functions. The first one is the net input function, which takes as arguments the input received from the different units connected to it. The second one is the activation function, which is fed the values yielded by the input function. Now, the input function determines how a unit processes the incoming signals. The simplest functions are weighted sum functions. And so, just by way of foreshadowing what we're going to say, to determine the net input to a node U, we simply take the sum of the values of the input signals for each of the nodes that output to U. So, for instance, the input signal to U from a unit is, how is it calculated? Well, it's the activation value of U times the weight of the connection between U and V. So usually the raw input from V takes the form of V's activation level at the moment. So you can express the net input signal sent from V to U as a product of the activation level of V multiplied by the weight of the connection between V and U. So suppose the activation level of V is 0.4 and that the weight of the connection at the moment is 0.3. What is the net input signal from U to V? Well, it is simply the product of the activation of V and the weight of the connection. So the net input to U from V is 0.12. This can easily be extended for the cases in which we have more than one unit feeding into unit U. We simply add the products of the weights and the activations for each of the neurons. So suppose we have also units V, X, and Y, all of them feeding into U. Then we first multiply the activation of V times its connection weight. And then we add the activation of X times the weight of the connection between U and X. Then we add the product of the activation of Y times the weight between U and Y. Again, let's go through a numerical example in which the activation values for three inputs are 0.4, 0.5, and 0.3 respectively, and the weights of their respective connections with U are 0.3, minus 0.4, and 0.7. Then we add the respective products, right, of the activation and weight. And then we end up with a net input for U, which is 0.13, as you can see. In general, you can express the total input to a given unit in a compact way with the sum notation. Here is the big sigma. In this case, where we have n units feeding into a unit I, you simply add for each of the units, which are the values of j there under the sigma, the product of the weight between I and j and the activation of j. For some applications, the input function for some of the units in some networks contains what is called a bias term. So the bias is a constant that is added to the input, and it allows you to shift the activation value in some direction. So sometimes you'll see that the input function is expressed in this way. However, we'll ignore this complication in what follows. Okay, that was the input function. What about the activation function? Well, the output of a unit ultimately depends on its activation level, right? But this is computed from the net or total input through what we call the activation function. So the activation level of a unit can be analog, if it's a number from 0 to 1, or we can be talking about a digital activation function, which it can be a 0 or 1, in which the unit can be on or off. And that's the analogy that it fires or doesn't fire, right? And the on and off is based on a sort of a biological analogy, right? It's a kind of an approximation of the all or none behavior of neurons. Now, in some models, the unit's activation value is simply some linear function of the input received. For instance, it might simply be the identity function, right? That the activity is equal to the input received. So here we have the input in the horizontal axis and the activation in the vertical axis. So we see that the output varies directly in proportion to the amount of input received, right? So it's just this line here. Or the function may be a little more complex. in this function, the activation is 0 until the input reaches a given threshold, and after that it becomes linear. Now, the input to a unit at some moment can be larger than 1. However, activation levels, and therefore the output sent, are often restricted to values from 0 to 1. In this case, we can use an activation function that squeezes, or sometimes says squishes or squashes, the net input into the activation value range. For instance, you have a very simple class, right? A simple class of a squeezing activation function. So this one works in an all or nothing digital way, and this is what is called a threshold function. Here the activation is either 0 or 1, depending on whether the input received equals or exceeds some predetermined threshold value, which is the theta there. In this case, if the threshold is met, the output is 1. Otherwise, it's 0. This is how it looks when graphed. Here the threshold would be 0. Any negative input yields an output of 0. But after 0, no matter how high the input, your output is going to be 1. So this function basically maps negative inputs to 0 and non-negative ones to 1. Another way of squeezing an activation value between 0 and 1 is by a logistic sigmoid function, which is evaluated for x by dividing 1 by 1 plus the constant e to the power of minus x. It's called sigmoid because its graph somewhat resembles an S. In this particular case, the lower inputs get mapped to a value close to 0 without actually reaching 0. But as we approach 0, it kind of gets closer to a linear function, right? And until we reach a plateau here in the upper values, which approaches 1 asymptotically. Now, there are other activation functions, but the threshold and the sigmoid are the traditional ones. So let's apply our activation functions to our previous example. So we have concluded that the total or net input received by U was 0.13. So we know its input, but what would be its activation value? Suppose that U implements a threshold function with a threshold of 0.25. Then, since the net input, which is 0.13, is smaller than the threshold, the activation value of U ends up being 0. So the unit U remains at rest. Now suppose that U instead instantiates a sigmoid activation function. Then we evaluate for the input value, which is 0.13. And the result is an activation value of 0.53. And that is how much output is going to be sending to the units it is connected to. And here we see a summary of the activity of a unit, broken into 3 steps. First, it integrates inputs from the previous layer to generate a net or total input value, right, in accordance to the input function. Then it uses an activation function to convert the net input into an activation value or activity level. And finally, it outputs this value as input to the units in the next layer. Okay, see you in the next video. Bye.